Welcome to the live stream. So I'm starting a little bit early just to make sure that everything's set up correctly. If you're here, please use the chat. If you haven't used this before, basically the chat is the way that I know that I'm not talking to no one, that you're engaging. You don't have to say much, but just something helps. So first things first, if you can say hi in the chat and just also let me know if you can hear me clearly or if I need to turn the volume up or down, etc. That would be very helpful. And then we'll get started soon. Let me just set up a couple of layers while I'm at it. And then we'll start having a look at some of the stuff through the assignments. So I've had a look through most of the assignments and I've found some common issues that I want to cover. And then after that, we'll cover the assignment part 2. So that'll be a little bit later on. So let me just put this together. When you join, say hi, chat. And then the plan for today is going to be 1, assignment 2, part 1, common mistakes. I haven't seen a perfect submission as yet, and most of them had quite a number of problems with them. And then we've got assignment spell 2, part 2, and then we might have a look at this week's lab if we get time. And then anything else you want to discuss. Want to discuss. So we'll just give a minute, we'll give 5 minutes or so for people to join. And then once everyone's here, we will start. And I'll just get this ready. So I've got the assignment here. It's good. That's the other common mistake. So we'll start it in 5 minutes. We'll start at 4. If you have questions, you can start posting them now. I've just got a big list here of things that I want to go through from what I've seen so far. That's the other one. Oh, that's so cool. That's cool. And might get the reference sheet up. Okay, reference sheet, beautiful. I'll need a pen. Copying. Values, mallocs is broken. better to put the choice calculation? Are you talking about the choice in terms of the calculate impedance in part 2? So in terms of calculating, we've got the modularity of having all of our impedance calculated in one function. If you take it out from that function, now it doesn't do what it is designed to do, and you can't take that to another program or use it for another use. It becomes single use. And so definitely the calculate impedance function is for calculating impedance. For the first one, it will work for any series. Doesn't matter what main is. You can change the program, you can use it in a completely different program, and it'll still work. And for the second task, same thing. Once we have a calculate impedance, like our multiply complex numbers, we can take that multiply complex numbers and put it anywhere. Your function is generic, and so calculate impedance, you can use it anywhere. The name specifically says calculate impedance, and so it's designed to calculate the impedance. And so to keep it generic, it should go in here. Yes, it may work if you put it in main, but now you've reduced the modularity of the program. Now you can no longer take calculate impedance and put it into another program, or use it again in your program if you need to call it multiple times. The whole purpose of calculate impedance is to calculate impedance. Okay, so definitely follow the instructions about where to put certain things. The calculation for impedance in the second part definitely needs to be inside of the function calculate impedance. Okay, cool. So we're starting to get some people joining us. We'll start in 1 minute. For those that are just joining us, I've got a big list of common mistakes that people are making in the first task. I got through about 50 submissions. There was about 150 submissions of part 1, but some of them I've given some feedback, some of them I've just written notes for myself so that we can talk about it now. And we'll go through the very common mistakes that most people are making, even if it was only a couple of people, so that you can pick it up. Okay, so let me just check something, because you might have one of the common mistakes. It shouldn't be the compiler because we're all using the exact same compiler and we're using the exact same system. So that shouldn't be a problem and we shouldn't have to worry about that. If you are using another compiler, I'm not able to help you because we don't have consistency between us. And that's why we're using a shared server so that we can debug between us. So if you are using another compiler, it's up to you to solve that problem. Did you submit the assignment? I can't see your submission. Oh well, we'll deal with that later. All right, so welcome. We're going to go through some things. The things are going to be assignment 2, part 1, common mistakes, and then we'll go through assignment 2, part 2. Then we'll go through this week's lab and then anything else you want to discuss. So I've got a list that I've kept as I going, and so I'm going to go through each one one by one. Some of them might seem silly, but everyone's at a different stage and everyone's at a different ability. So some of them might be a bit obvious for some people. So the very first one that I've noticed on a couple is the password. Okay. With the password, there's one password per part. Okay. And just don't put 3 passwords in each one. It's one password per part, and the password needs to be included. Okay. All right. So that's the first note that I will give you. Now, the second one is always initialize rather than declare when you have the option. Okay. This is important because it will save you time in testing. It will make it easier to debug your code. It reduces the cognitive load of the reader. And so basically what I mean by this, if let's say I said to you, create a variable called a as an int and set the value to 6. And if you did something like this, whilst correct, it's not very good practice. If you've got the option, always initialize. Okay, so we can just set this to 6 straight away. Sometimes we don't have the option, such as scanf. Okay, we don't know what the original value is going to be because we're getting it from the user. So when we have that option, we can't initialize it straight away. But when we do have the option, we should. So for example, I've seen a lot of students do stuff like this. Float, star, table, and then they'll write table becomes float star, malloc, blah, blah, blah. Okay. Here you can see there's nothing that requires us not to initialize. Okay. So you can easily put these all on one line and clearly see what the value is right at the start. This table never has an uninitialized value. Okay? So if your mallocs are done after the declaration, fix it up and just clean it up such that you do it on one line, such that it be float, star, table becomes float, star, malloc, blah, blah, blah. Okay. So when you have the option, always go with a single line. Okay. This will also help you in enforcing that you put things in context. Okay. Which is the next thing that we're going to talk about. Okay. We've already run out of room. Wow. Maybe I didn't make this big enough. All right. Declare in context rather than everything at the top. And when you can limit scope, do so. Okay. So in terms of readability with our scientific computing, we generally have a lot of variables in scientific computing. We're usually dealing with mathematical problems, and mathematical problems generally have a large amount of data and variable data. And so it's a lot more manageable to declare things in context. It makes it easier to read, and limiting scope makes your program more safe. And we've talked a little bit about this, but I've still seen people going about declaring everything at the top of main, declaring everything at the top of the function. So try and avoid that. there's not too many places in this program that we can actually limit scope. There's only one or two. But for example, if you've got a for loop, okay, you can declare the I just before it. Okay, you don't have to go all the way to the top. Should the password be on a new line? Yes, the password should be on a new line. As long as it's there, so you can put a new line after you're printing your name and so on. I'm not really worried too much about that. As long as the password's there, we're actually parsing the C file for the password, not the output. So it doesn't actually affect what it's used for. So we don't really care what it looks like, the password, when it prints. It's more that it's included in the file. All right. So them three I've covered. All right. So now I'll talk about the next one, which is important. And this one, basically, if you're doing this, you've definitely lost a large amount of marks already. And this is when it comes to using your for loops. And I've seen this actually a couple of times already. And we'll have something. So I'm just going to make it simple. Scanf. We're getting the components, let's say. Okay. You'll have some other things before and after this. But what I've seen some students do is basically starting I from 1. Okay. Up to n I++. And they've done this. Okay. So this is bad. Okay. Firstly, our indexes always start at 0. But the reason that you'll notice in the output, it actually says to the user, enter component 1. Okay. Now, this is basically to make it easier for the reader and the user, because the user is not always going to be literate in computing. Okay. If you go to an ATM machine, you can't assume that the user is always going to be a master's of IT. Okay. It could be anyone. It could be the gardener. It could be someone that's experienced in history. It could be a 12-year-old. Okay. That's the reason that we print out to the screen 1, 2, 3, 4 to make it easier for them to understand. And with natural counting, we start at 1. Okay. If I say what's component 1, that's usually talking about the first. But from the computing perspective, we start from 0. Okay. And so your for loops shouldn't be starting from 1. They should be starting from 0 and going up to n. Now, if you want to print to the user a more logical value for their domain and world, then with your printf, if you need to print a number, you can do so by just printing I plus 1. Okay. So don't bend the code to the user. Okay. Rather just print to the user such that they think that it's the first one. Okay. The indexes are not going to make sense to the user. And you can think about that in terms of natural language. Okay. If I said, this is assignment 1, versus if I said, this is assignment at index 0, a lot of students would have been confused. Okay. And that makes sense. Like, I didn't write that on LMS. We didn't write assignment index 0. We wrote assignment 1. Okay. But in the database, it could be stored at index 0. Okay. So that's another common mistake that a lot of students have done. And why this is bad is because you're actually accessing illegal memory. Okay. Because let's say your array is 1, 2, 3, 4, 5 bytes long. Okay, just imagine it's a car array or something, and you start from the second one. This very last one that you access, you shouldn't have access to. Okay, and that might be some other part of your program, and it most likely will be. And this is why you probably, if you have done this, you won't see your program crash, but you might see some undefined behavior because it's very close to your program. Okay. So that's the next one. And most people that did do this mistake did it throughout their program. So they did it in the getting the components, in the impedance, in the printing. So if you're starting I at 1, you definitely need to go back and check your code. There are a lot of marks associated to safe behavior. Okay, and we talked about this in the lab, the fact that just because it works isn't good enough. All right, so I won't repeat that for the other ones. So now we'll continue. So the next one is just a little bit of professionalism with scientific computing. We're using Ullmann style, and all that means is that the braces go on the following line, okay? Not here, okay? Now, I know that you might have used other languages where the braces are here, but we're all following a set standard, and you as engineers or masters of IT should be able to conform to a particular standard that's given to you in a company or in a scientific workplace or environment. Okay, so the standard we're using is Ullmann's. There's no brace here. The other standard that we're using that we haven't talked too much about is we always include a brace even for single lines with our scientific computing. Okay, so even if it's a single line, still include the braces. Okay, makes sense? All right, are we all good up to this point? If you're all good, just put a thumbs up, an animal, a yes, or something like that. Or if something's confusing, let me know. And then we'll get on to a couple of really, really important ones. How can we print the string in the center of the row? I think you need some variables on LMS are in camel case. Which variables? Which variables? Can you tell me which variables? There shouldn't be. It could be real sum. Where's that? I don't know where you're talking about. Can you point to exactly where you're talking about? Imag sum and real sum on LMS? I can't see it. I might have made that mistake, but I can't see it. All right. How can we print the string in the center of the row? Can you clarify what you mean? I'm not 100% sure what you mean by that. All right. All right, so the next one, and I have seen some amazing solutions for this, and they're just a complete waste of time and effort, and it's really disappointing to see people waste their time on this. So with the output, you'll notice that, and I'll cover two common mistakes here. We've got something like this. We've got plus 0.000 E E plus, sorry, we're using Unix 00, close bracket, plus minus 5.305 E plus 00, close bracket, J. Connection loss. Okay, I'm not sure what you're going on about. All right. So some people have gone about this in a very, very strange way. And they've tried to make a function that does this, but there's no need whatsoever. Okay. We did lab 1, part 2, or lab 0, part 2 in week 2, and we talked about a couple of things here. So we've got this here, which is scientific notation. Okay. We've got this here, which is a sign flag. Okay. And we've got this here, which is precision. Okay. So let's go to the lab reference and let's have a look if we have all of that stuff. I'll just grab the part that I need, the lab reference. Beautiful. All right, so I move that across over there a little bit. So let's have a, oh, I'm running out of room. That's okay, I don't need all that. No, actually I do. Oh my God, why am I running out of so much room? All right, we'll go up here. I gotta make this canvas bigger. We'll get to that. All right, so first thing is scientific notation is we have to print that string in the center. What would we have to do? Oh, okay, that's... All right, so %E is scientific notation, okay? So we know how to do that. We have flag width dot precision. Precision is the number of digits to display. And then the flag plus always displays a sign. So if it's positive, we show a plus. If it's negative, we show a minus. So this should be fairly easy to implement knowing that information. So we can do something like bracket % plus 0.3 E, close bracket, plus, and so on. Okay. Notice the plus is in the inside because that's the flag. Okay. This stuff is examinable. That's why we did a whole lab on it. Okay. There are there are 4 flags. Okay. You've got the minus flag, which less justifies. You've got the plus flag that shows signs. You've got a space one that shows a space if there is no sign. And then you've also got pad with leading zeros. Okay. So you need to know the flags. All right. But I've seen some people do if statements, checking if it's positive or negative. You just wasted a bunch of time. Okay. And just because you wrote a lot of code doesn't make it good. And it doesn't show a good understanding. It actually shows a poor understanding. All right. If you need to print in the center, there is no center justify like Word or something like that. So you need to calculate where you want to print in the center. So if I want to print, let's say, the letter C in the center, I can fill this with spaces until I reach the center. Okay. Or if I need to print a word in the center or something like that, the other way I can do it is I could use a width specifier such that it will always take up that amount of space. But for this assignment, just using spaces is perfectly fine. It doesn't really matter either way. No, you cannot, because, okay, so someone asked, and this is the misunderstanding of the week 2 of this subject. We cannot do this. This will print a plus. That's just a character. It's not part of the format specifier. This plus always displays a sign. If the number's negative, it's going to print out plus minus. And if the number's positive here, it's going to print out plus and then the number. So no, you cannot do it this way. Does that make sense? All right. If you need some practice with this, go back to week 2, and there was a lab on this. All right, now where's my list? All right, so that's the sign flag. We did almond style, we did that. All right, so this one, I've seen a couple of people do this. This one's a bit strange. So with our functions, they have a particular functionality, okay? And the reason we're using, oh, I lost my audio. The reason that we're using the functions in our program is to make our program a little modular, such that we've got some functions that can be taken out and used elsewhere if needed. And we've got main, we've got our calculate, if I can spell, Z, and we've got our print results, I think it is. And then we've got a bunch of support functions, which are for calculating complex numbers. So we have all of these. Now these complex numbers ones, you notice they're really modular. We could move them from one program to another program, and we'll even learn how to make these even better later on. Well, you can make them better later on by creating your own header file. But with this, okay, with one of these, let's say I had complex addition, and I print the result in there. Now it's no longer modular, and I can't move it between programs because it's just printing random stuff in the middle of my program. This function here is calculate impedance. It does two things. It calculates the impedance of each individual component and the total. For the first one, it just works for series, and the second one, it just works for parallel. It's not a printing function. It's not a displaying function. With our functions, and this also applies if you're doing something like, well, really any language. When you're creating functions or methods, you need to think, are they an interface function or are they a calculation function or an operation function? If they're an operation function or a calculating function, don't include prints in them because you want your prints to be either in main or in functions designed specifically for interfaces and design interfaces, and it fits in with your design. Okay. So don't have any of your printing inside of the calculate, and don't have any of your calculations in the printing. Okay. That I've seen, it's not many students, but just a couple have done that. They put the calculating impedance in here, or they've got some printing in here. Some students have forgotten the print n and they've done it all in one function. Some people have done the total in here. That also won't be accepted. Okay, you won't be marked for that because we're marking based on functions. Okay, so make sure you're following the instructions about where things should go. All right. All right, typecasts. So in one of the calculation, we had something like 1 divided by 2, 2 times pi, I'll talk about this pi in a moment, times, I think it was values, pi times frequency. Yep, that's reactance. That was a minus at the top. All right. And I've seen some people do this. Oh, actually, let me do this. Double minus 1 divided by double. Actually, most of them had it inside of the bracket. Times pi times values, blah, blah, blah. What is the largest type on the denominator? Values is a double, so there's no need for the typecast. Okay. You can put 1.0 here and 2.0 here if you want to make it slightly faster, but typecasting is redundant. Okay, it's not going to do anything because your largest type is a double anyway. Everything's going to be converted to a double eventually if you have a double in either your numerator or denominator. Double is the largest type, so everything will become that. Okay. All right, we'll talk about that. Maybe I'll do that now. All right, so now I'll talk about pi. And I'm going to show you the best way to do pi. And this is actually the official way that it's done in the math library, but we're not using the math library. So we're going to do our own, okay? And what you need to do is you need to go to use a, there's 2 ways we could do this. We could use a symbolic constant, or we could use a const. Now a const is a variable, okay, where a symbolic constant is a macro. Okay, so a macro basically is just a name that makes it easy for us to read while we're coding, but then it'll just change it into the value. A variable that's constant has very specific uses, such as we need the address of it, or we want to be able to treat it as a variable, which we don't want to treat pi as a variable. It doesn't change. We don't need the address of it. We don't need any special part of it. So we'll just use a symbolic constant. And the syntax for the symbolic constant is at the top of your code. So after your hash includes, okay, blah, 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 standard IO, standard lib, hash, define, pi, and then put a space and then write the number 3.14152.9265359. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Beautiful. Now, this allows you to use pi wherever you like in your code, and the preprocessor will just replace it with that number. Okay, so if I write something like float a becomes pi times 2, okay, all the preprocessor will do is it will swap that pi with that number and then send it to the compiler. Okay. All right. Now, if you put a semicolon after it, you will get an error. And it will be hard to find because the compiler doesn't look at hash defines or hash includes. They're handled by the preprocessor. And so you won't be able to find the mistakes here. Rather, the mistake will be here because what the preprocessor will do, it will write 3.14592655359 semicolon times 2. Okay, whatever you write here, it's just going to put in that space. So don't put a semicolon there. All right, and that's how you should do pi. Okay, make sense? Any problems with that? The other thing is that macros should be capital, okay, so that you know that they're a macro. Definitely no equals sign. So once again, if you put the equals there, okay, and I did float a becomes 2 times pi, what the prefiler will do will change that so that it is 2 times equals. And it will actually ignore the value after that because it's separated by a space, okay? If you didn't have a space there, then it would put equals in the number. Obviously, that doesn't compile, okay? Whatever you write here will be go here, okay? So if you put an equals there, then it will go there, okay? So you can do cheeky hash defines if you want. So you could do something like printf, hello, but that's not a very good use of hash define, and we don't want to see that. But you could put that there, and that means anytime you write print, it actually prints hello. Okay, you can play around with it, but don't be stupid with it because it's just going to make your code unreadable. Okay, but definitely no equals, no semicolon. All good? Does that make sense? We all happy with that? Let me know if you're all happy, and then we'll go on to a couple more mistakes. And then, where's my list of mistakes? It's here. So typecast, we're done. All right. I'll leave that one till last because that one's the big one that nearly everyone did wrong. Redundant coding printing. Oh, yep, cool. So another one was with the printing. So I might just go over the printing again, just to explain how it works. So we have, I'm trying to remember how it looks. We have a table, okay? You can think of a table like on Microsoft Excel or something like that. And it has 2 rows. Okay? And then it has a bunch of columns. Now, these columns here in the middle are dynamic. So if I have 3 components, there's going to be 3 here. If I have, let's say 1, 2, 3, 4, so 5 components, it's going to be this big. Okay. All right. But those 2 outside parts are always consistent. Okay. Doesn't matter how big it gets, we've always got those. So you can think of it like a sandwich. Okay. You got the bread on the outside, and then you can have as many fillings as you like. All right. So here, what we are going to do is what we're going to do is basically this, and this are just prints. Okay, and to keep it simple, you can just make them prints. We also need to remember. What is going on? We also need to remember that we only can print this way. Okay? So we know also that there's a new line here and there's a new line here. So let's build this structure. So this part here is going to obviously be first. We've got a printf. We'll ignore this part. Okay, so something dynamic. Then we printf. Okay. Then we print a new line. Then we've got something that's static again, so we can just do another printf. Now I am doing a lot of printfs here. If it makes it more readable, that's perfectly fine. And then we've got something that's dynamic, something that changes. And then we've got another printf. Now, this, another color, this color here, this one here, I think it prints, let me double check what it prints. It's something ohm Z. I'll write it exactly. So this prints Z ohms. So that's just a literal Z ohms. This one here at the end prints the total. Okay, so this is going to be one of those brackets with brackets, brackets, blah, blah, and then 2 arguments. Okay, and we remember that the very last thing in the table is going to be at index n, because when we malloced it, we added 1. Okay, so normally n wouldn't be good, but here it's okay. Okay. Oh, shit, actually, that's not the right place for that. That should say total. Sorry, I've skipped ahead. In this one, it should say total. Sorry. This one says total. This one says Z ohm. No, this one says, what does this one say? Oh, this one says components. Sorry. Components. I'm doing the bottom one. Looking at the wrong. Z ohms. Sorry. Too many screens open. This one says components. Components. This one here said Z ohms. And this one here prints the total. And here we'd have 2 arguments for our totals, both real and imaginary. Okay. Then we've got this dynamic part inside of here. Yep. Now we've got this dynamic part in here. Now, because it's dynamic, it's going to change each time. And this is basically a for loop. Okay. So basically, if it's 3, we go around it 3 times. If it's 5, we go around it 5 times. So we can create a variable. Let's call it I. Okay. And then we can just go around that for loop dynamically. For I 0, I less than n, I plus plus. Go through that. And here we're going to have an if, else if, else, and we're going to print either R, C, or L. Yeah. I think we've actually got I. That's actually wrong. But yeah, we're going to print I then. If you print I or L, I don't mind. Depends which notation you're using. And then the same thing down here. It's also dynamic. Now, there is no, and you will lose marks for this, there is no reason to use J here. It is still a single dimension. We can reuse I. There is no need to use J here. Okay? And then we can just print each of these. Imaginary I. Cool. Now, if you want to combine the total together, you can, but for readability and to be able to take the total out, feel free to leave it out. Personally, I think it's a little nicer having it out because it's not part of the components. It's the total, so it's actually a separate value. But either way, it's up to you. And that's our print function. And yours should look something similar to that. You can do some tricks if you like to get it down smaller, but basically that's what your functions. Yes, the videos are available later if you need to come back to them. All right, so what was the next one? Sorry, where's, there it is, cool. All right, okay, so the next one is, that was a common mistake, was pointer arithmetic. And my advice is not going to be, let me just start a new file. This is just, I don't know where anything is. Where are we? There we go. All right. So my advice with pointer arithmetic, if you don't know how to use it yet, don't. Okay. So for example, there's two ways you can do stuff. You can do it with or without pointer arithmetic. So let's take an example of just getting values from a user, like you are with your components. So if I have int star a, int star malloc size of int times, let's just put a constant there. But then you have a for loop. I equals 0, I less than 4, I plus plus. Now, this is obviously not dynamic, but you know how to do that. I'm just trying to speed this up a little bit. And then you have a printf, enter %d, and then you have I plus 1, like you have on your assignment, and then you have some scanf. Okay. And here, you could do this two ways. You could do %d and then just go the address of a I. Okay. You notice that I didn't make a copy. I didn't use any dereferencing. And same when I go if a I is a 1. Okay, so I'm just doing basically what your assignment is. So what you'll notice here is there's no pointer arithmetic. Okay, pointer arithmetic is faster, but if you're not comfortable with it, just use square braces. Okay, as soon as you malloc some memory, it's an array. It's contiguous memory, so it's an array, and you can use your square braces like you did before. Okay. So please be aware of that. If you are uncomfortable with pointer arithmetic, I'm not going to show you the pointer arithmetic version because I'd much prefer that you do this first and get that working than worrying about the pointer arithmetic. If you don't understand pointer arithmetic, there's like 8 examples in the lab from last week. But if you don't feel comfortable, don't make a pointer position or pointer copy. Don't worry about that and just use the square brackets. Okay, it works exactly the same. It's just a bit slower. Okay, and then you can go, if it's a 1, then I think it's another scanf. I can't, yeah, I think it is enter in ohms or something like that. And then you can do %f, the address of values I. Okay, so you can do it either way. Okay. So if you feel uncomfortable with pointer arithmetic, You don't have to use it. We used to make students, enforce students to use it. But if you're not comfortable, do it this way first. Or even if you are comfortable, do it this way first and then do it the harder way after. All right. So don't be afraid to use the square braces. You don't need to use pointer arithmetic. Pointer arithmetic is a lot harder because you have to deal with a lot more variables. Okay. So as I said, just feel free to use square brackets. If you want to use an extra function for getting the components in, feel free. Just be careful. Okay. Cool. All right. So those people that are guessing and trying to get that working, and I see a lot of students going straight to pointer arithmetic, which doesn't make much sense because just using square brackets is so much easier. Okay, you're just making it hard for yourself. All right. Okay, so variable names is another one. I've noticed a couple of people doing this. Int z for z equals 0. And every time they have another loop, they create another variable name. Okay, this is not acceptable. Okay, there are standard names or descriptive names. And the standard names include these. Why is it still on that? You got I, J, K, which are indices. Okay, you've got N and M, which are sizes. Okay, N is for 1 dimension, M is for 2 dimensions. I is for 1 dimension, J is for 2 dimensions, K is for 3 dimensions. Okay, any programmer should be able to read these and know what they mean. But if you put Z in there, no one has a clue what you're talking about. And if you go show that as part of your portfolio, they're just going to go, what the hell's Z? Okay. So make sure if you're going to use standard names, use them, but don't introduce other ones that no one around the world will have a clue what you're talking about. Everyone should understand what these are. And if you use these incorrectly, you're going to confuse people. Okay. For example, in this program, there is no need to use J. If you use J in this program, you are going to confuse people. All right. And same with M. There's no M in this program because everything's single dimension. All right. What's the other one? Oh, okay. So I'm going to go through one more mistake, and then I'll go through the final mistake that nearly 95% of students made, which is the big one. And we'll talk about it because it's an important one. So I'll just go through one other mistake. I think only 1 or 2 people got this wrong. With your malloc, if you're using the format of size of type times some n, okay? That n, if it involves a calculation, so let's say n, this is math here, okay? If n was 2x plus 2 or something like that, you need to bracket it, okay? And so with our n, we had x plus 1, so it needs to be bracketed, okay? Because, so we used n, so little lowercase n is my x in this case. Basically, if this isn't bracketed, you're just going to add 1 byte to the end of it, okay? Rather than another one of these types, okay? And you will lose a lot of marks. All right. If you're still with us, just say that you are. I'm I'm just going to have a quick 4-minute break, and then I'll go over the big mistake that most students, I can't even spell. 4 minutes break, then go over mistake. Right, we have audio again. All right, so I got quite a few people here. That's excellent to see. All right, so first thing, for printing components in 101, blah, 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 I can use spaces or width. So you can use spaces. You can also use width. There's actually a really good way of doing it, but I'm not going to show you here. If I'm in the lab and you want to see a slightly better way to do it, let me know, using width. But you can use width. You're not really going to get away with spaces at the moment anyway, because if you use width, you still need the spaces after the character, because there is no center justify in our standard format specifiers. You could width a space, but I think a space is just more readable. Invalid type argument. Unary star have double. You can't dereference a double. That doesn't make any sense. That's what it's saying. you have a double and you're dereferencing it. Most likely you have something like star A square brackets I. I've seen a couple of students do that, which makes no sense because all that's saying is star star A plus I. Unless this is another pointer, which we don't have double pointers here, this makes no sense. So that's most likely your mistake from that error. All right, now let's go over the big one. So a lot of people forgot to include complex addition in their first part one. Yes, it did help. Wow. All right. So make sure, yes, that helped, but make sure you understand why it helped, okay? Because putting stars randomly is not going to help you in the exam because you won't be able to check them. All right. So a lot of people didn't actually use complex addition in the first part, but it's set up brilliantly to allow complex addition to be used. And the task is set up very, very well for it, such that it is very modular, and we can easily use it to make the program really readable. So we have some kind of summation, and we've got this summation of A I plus B I J. Okay. And we know that that summation is, now this is maths here, so I'm starting my indices at 1 for mathematics, is just going to be A1 plus B1J plus A2 plus B2J plus blah, blah, blah. Okay. So we know how this works, okay? And we also, some students have just added these up by themselves and then added these up by themselves, but we've got a complex numbers function that we wrote. So why wouldn't we show off our skills and use it? So let's have a look at this, and let's put some values in here. So let's say I've got 3 complex numbers and I want to add them together. And I've got 4, 2, 8, 1, 2, 2. Okay. Now, with this, we can clearly quite easily see that we've got 14 plus 5, J. Okay. But we may be able to do that quickly, okay, in our heads, but with a computer's a lot faster, but it has to do the operations a bit slower, okay? Isn't mandatory to use complex addition. My thing worked without using it. So this is what we were talking about earlier. So this is really, really important. Just because something works doesn't make it good. Okay, you are going to be competing with a lot of students in the future, and just getting an output. Yeah, we could teach anyone to get an output. We want quality, master's level or engineering level quality work, and you should know how to use your functions. If you don't know how to use your functions, then they're pointless. You might as well go back to week 4 and not use pointers at all. If you don't know how to use your functions to make your program modular, then you don't really understand your program that you've created, and you shouldn't really include it in a portfolio of your work. So it's not mandatory, but it's going to be a bit disappointing that you don't know how to use something you've created. So I would say everyone should use it because they've got the advantage. They've got that tool there. They've got that function, which is theirs. And if you've created it, you should be able to know how to use it. Just because something works, and this also applies, just because it works doesn't make it right. And just because it works doesn't make it professional. Okay. For example, imagine if your bank internet banking was designed by a first-year undergrad. You wouldn't feel very trustworthy of it. It might work, and it might work perfectly, but it might look like it's done by someone that's not very professional, and so you wouldn't trust it. Okay, so you need to have your work professional. So let's go back to this problem. So we want to add these up, and we want to do it with a computer. So there's two things that we need to know with our computer. We only have binary addition. Okay, binary addition means that there's two operands, okay, and one operator. And we need to store the result of that binary addition after every addition. Okay, so let's have a look at this. All right. So here, we want to start off our summation at 0. Okay, and this is a general rule that applies with any language. Basically, whenever doing summation, always start at 0. Whenever calculating the product, always start at 1. Okay, it will make it a lot easier for you. So we start at 0. Okay, and then what we do is we need to do our binary addition. Now we can only do an addition of two things at once. So the first thing we're going to do is we're going to add this 4 and this 0 together. We're going to go 0 plus 4. And with that, we need somewhere to store it. Now, I've created this storage space here, and I've got the value. Remember, with C, we can write something like A becomes A plus 2. Okay, we can use the value and then store over it. So we're going to do that. Okay, so we'll store the result back in here. So we get a 4. And then we do the same with the 2. So we get 0 plus 2, and then we store the result here. So we get a 2. We get a 2. And then we move to the next number. Okay, so we got an 8. We grab the first one, which is a 4. And we add it to the 8, so we get a 12. Cool. And then we do it with the next number, so we get a 2 and a 1. Okay, and we get a 3. All right. So here, what we basically have is something like some real becomes some real plus real I, and some imaginary becomes some imaginary plus imaginary I. And it's in some kind of for loop. And this is how most students have written it. Okay. I 0, I less than, and then n, I plus plus. And we need to declare this some real and some imaginary. Double some real 0, double some imaginary 0. So we could do it this way, but as I said, we're a lot smarter than that, and we have the power to use our own functions that we've created. There's no semicolons there, but I'm going to get rid of it anyway soon. All right, so we have this, but this breaks everything down to 2, and it's not really clear that we're dealing with complex numbers here. We can make it extremely obvious, and we can make it extremely obvious that we're doing complex addition by using our function instead. So let's have a look at our complex addition function. It has 6 arguments. Okay. Now, what's going in, given what we did before? We have some real, some imaginary. The second part is going to be the real I, and then the imaginary I. The last part is where we want the answer back. Well, we want it here. So we pass the address of some real and the address of some imaginary. So let's get rid of all this. Let's do this our way, using pointers and a nice function that shows that we're doing complex addition. So we've got complex addition. I'm just shortening that because I have to write this using a pen. So real I, obviously yours is impedance underscore real something, blah, blah, blah. Imaginary I, we shouldn't give those both I's just in case someone actually does do it. And then some real, and then the address of some imaginary. Done. A lot better, a lot clearer, and it's actually really nice because you got the really, really nice feedback loop there that anyone that's a little bit experienced can clearly see that really nice feedback loop of these are coming in, this is coming out, this is feeding back to here. Okay, so anyone that's done a bit of electronics or something like that and understands a feedback loop, it's kind of nice. But it's just summation. It's just summation. Cool. And then after that, you can put your sum real into the correct spot. It should be at the end location. Some real, some imaginary. You can actually use the n while you're calculating, but to reduce the complexity, it's probably easier just creating this other variable. Cool. Does that make sense? So you should be able to fix that up quite easily and make this a little bit nicer. And then it shows that you understand this complex addition. And make sure you do understand it. And I would definitely draw a box and pointer diagram for this to really understand what's happening here. Because if you understand what's happening here, it makes part 2 a lot easier. Okay. All right. So let me check my list. If there's anything else. Okay. I actually did miss a couple of things. Let me just cover 1 or 2 others. So a couple of other common mistakes. Well, these ones weren't so common. There were just a couple of students. Components is a dynamically allocated array. N is the number of components. Some students got confused and tried to use this as the number of components. This is actually storing a value that maps to a particular type of component. So 1 maps to resistor, 2 maps to capacitor, and 3 maps to inductor. And that's definitely the description that you should be giving there, where N is the number of components. And if you feel more comfortable, you can change that so it says number of components. Values and components need to be dynamically allocated. Some people I think they watched the video and they're just kind of don't know how to do reading without the video. You need to read the steps. They need to be dynamically allocated as well. So you need to work out how to do that, and they involve malloc. Okay. The other one was in the picture. It looks like there's triangular brackets in the answer. They're actually round. I think that's it for the common mistakes that I had written down. Has anyone got any questions about part one other than that? If no, just say no while I get part two up. Part two. What was the real n thing you did before? So when I did real n, I'm talking about the real part of the impedance. So what you've got to remember is that typically with our arrays, we never ever reference n. So if I go int a4, okay, we'd never usually write a4, okay, but the reason that we did is because we did something like this in our malloc, such that I can write a4. Okay, so it's just the last one. It's because I added the 1 at the end. Is the whole assignment due May 10th or part 1 due earlier than part 2? No, the whole assignment is going to be due. So because how many people submitted it, I'm probably going to move it to Sunday midnight. Not this Sunday, 12th. Okay. And because so many people showed up for help session and so on, and so many people submitted the assignment. So the whole thing though, and I'll hopefully have the assignment 3 written by then. I was going to do that today and I ran out of time. So hopefully I find some time tomorrow, because I really need to write that. Because we're in, what week are we up to? Week 9, week 10. Yeah, cool. Yeah, we've got heaps of time. All right. All right. Part 2. Let me do a copy paste of part 2. All good so far. Is there any other questions about part 1? So we're going to go into part 2. It doesn't have any questions. There's no bad questions. All right. So let's start having a look at this. So only start this once part 1 works completely. Okay. Check your program against the test cases given on LMS. So there's a bunch of test cases on LMS, and you can check them. Make a copy of part 1. Okay. If you accidentally start writing over it and start writing part 2, you have to go back and fix it, because if you submit 2 part 2s, you will only get marked for part 2. Okay. You're confused about printing sum. that the print? No, that's not the print. So once you so with your array, so you had Z real, Z imaginary, okay? And this had 3 components, let's say. This might be 4, 2, 6. This might be 8, 1, 3. And we did the maths, and this last one was the total. Yeah? N here is 3. Yeah? We did the maths, and this came out as 12. We did the maths, and this also came out as 12. And so when we want to print the total, we print at index n. Okay? Remember, the index starts at 0. And that's how we print out the total. Okay, we're just printing out the last one. Okay, so you got your brackets, you got your plus, you got your format specifiers. Okay, you've got your table that you created, and then table, real, blah, 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 n. And then table, imaginary, n. Okay, I'm not writing the full name out. If you don't know what they are, then you need to go back to the start because you're not up to this stage then. Cool, excellent, excellent, excellent. That's done it. No, this is the printing. Oh, the calculating of it is done in the addition. So it's in the calculate impedance function, and this is the total calculation part. Yes, 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 yes. So this is just for the printing, but yes, you're right. But the printing goes in the print function. All right, you need to rename this to part 2 and modify this for part 2. Okay, so don't accidentally modify part 1. Though if you did, you could easily just switch the names around. All right, so the difference here is that we're going to have some choice. Okay, so this is more like the first assignment where the user could choose they wanted to go radians to degrees or degrees to radians. Here we want either parallel or series. Okay. There's a worked example here that Bella put together, and there's example outputs here. Make sure you understand the math before continuing. If there's something bothering you about the math, let me know. But hopefully the math isn't too much of the work. Where are we? All right, let me get the next part. All right. So the next part is our function prototypes need to change. There's only one change here, and this is the last one. And I might actually talk about this while I'm here because some people either didn't notice this or they got confused by it and just didn't say anything. When you see this, I'm on the wrong layer. When you see this, int c square brackets, as a parameter, it's exactly the same as this. Okay. So that's why this here, with the double star, we could have rewritten it with a square bracket. With 2 square brackets, it's a little bit different. And we'll talk about that difference later. 2-dimensional arrays are very, very different, okay, than single dimensions. And a lot of people don't realize that, how different they are. this here is just a pointer to the start of an array. As we saw, this is just a pointer to the start of the array. There is some slight differences on how we can use it, but for you, just it's fine. Okay, just think of it as a pointer. I just kind of did that so you could see that they work pretty much the same. So yeah, but the important thing here is choice. Okay, so what this shows us is that our function calculate impedance is affected by this choice because it needs that information. So remember, when reading a function prototype, it actually gives you a lot of information. And once you become experienced in looking up APIs and stuff like that, you'll be able to look at a list and you'll be able to look at a prototype and go, oh, this is the prototype I need. This has the right information. This is I understand what it's doing. Okay. So then we get to main. Okay. And there's not much changes in main. Main fairly easy. Modify step 2. So now the other thing that isn't here but you need to do, change the password. Okay. That's the other thing you need to do. But modify step 2 in part 1, the program also asks the user, firstly, which circuit they would like to evaluate. And this is choice, so you can store it in a variable named choice or user choice or whatever you want to call it. And the other thing is that before it said how many components are there, now it says either how many components are there in parallel or how many components are in series. Okay, it's just an if-else statement there based on their choice. Okay. 1 is parallel, 2 is series. No. Okay. Modify step 7 of main, part 1, such the function is called properly. So you just need to add one thing, one argument. You need to send choice to the function. And that's that. Now, print results for the second part. It's really important that you get it working correctly for the first part because there's no modification for the print results at all. Okay, you shouldn't have to change it whatsoever. Okay. So then we get to the fun part. Now, there is actually quite a few different ways you can solve this problem. Okay, and different years we've given different ways to solve this problem. You've got one of the easier ones, but still it's a little bit interesting. So I'm going to copy and paste this. Then I might go have a quick break and we'll cover this. So I'm just placing this. I'll start a new one. All right. All right. All right. So what I'm going to do is I'm going to have a quick break. And if anyone is a little bit behind, go up to the live portion so that you're at the same speed as us, because I want to talk about this together with you. So let's have a 6-minute break, and then we can go through this together and really understand this, and that will give you pretty much everything we need. Okay, and this will be really, really helpful for part 2. And then once you've done that, you've got the week to work on part 3, which is a little bit more difficult, but is worth about 28%. So the first and the third are worth the most. The second part is worth 10%. So we'll talk about this. All right, so let's have a quick break so that anyone that's a little bit behind can catch up. If you're still here, just say so in the chat, just so I know you're still here. And I'm just going to mute this for now. All right, you should be able to hear me now. Let's get into this. All right, so get rid of that. So let's go through this, and let's actually, I might grab the calculation because it makes it easier for me. Nice formula, beautiful. All right. So this guy, and we've also got this guy. Okay, so we've got two formulas here. I'm not going to worry too much about the steps because we don't really need the steps. And we've got series and we've got parallel. Okay. Damn it. Let's go up here. Just going to move to the top of this page. So we've got a bit more room. Hey, we are at the top. Beautiful. Move out of the way. All right, cool. So we've got series and parallel. I put series on the left. Yeah. And with this, what we can firstly note is that they are very similar, but slightly different. Firstly, we can ignore, well, firstly, we can't ignore, but if we ignore this part here, they look very, very similar, okay? The only difference is that this is inverse, okay? So the summation part is going to be similar as well, okay? So using what we know about our summation from our previous one, we can do something similar, okay? So what we're going to do is so for both of these, we're going to need some we're going to need some sum, okay? So we can do double sum real and start it at 0, okay? Because as we said, for any sum, it doesn't matter what the sum is. We're going to need some sum, okay? Then we know for this one, okay? Now, the notation that I'm going to use to keep this simple on the screen, I want you to use better names, but just because I need to make this small, I'm going to use SR for sum real, okay, and SI for sum imaginary. Why am I in the bottom layer? You should have proper names. Okay. So let's put that note there. I keep going between layers. All right. So I'm going to create an int I. Okay. And then I'm going to create a for loop. Okay. I less than n, I plus plus. And we've got our complex addition. Addition Okay, and we had Z. No, we didn't. We had some real, some imaginary. We had Z real, I, and we had Z imaginary I. And then we had the address of some real. And then we had the address of some imaginary. Okay, and that's what our series looked like. Okay. So that's going to be helpful because I'm going to have to make this pretty small because I need this side for our other part. So hopefully that's still readable there. So for this, we know we're going to need a for loop as well. Okay. But we need to do a little bit more work. So let me actually I can do yeah. So here, what we need to do is, let's say we've got, let's say we want to go some, would help if I'm writing. I don't know what's going on. But let's say if I wanted to do sum of 2 plus 2j, and 1 over 4 plus 4j. Okay. With this, we know that we can only do binary operations. Okay. So this can only work on 2, and so can this. This division can only work on 2. So we need to make a decision. Should we do the division or the addition first? Well, we have to do the division first because of BODMAS. Okay, so we're going to do the division first. Now, this is complex division, and we've got 1 up the top. So what's the complex part? 0. Okay, and we can write that in, okay, to make it a bit clearer. And what we want to do here is basically we want to calculate this and then add this to our sum. Okay. And then we want to calculate this and then add this to our sum. Okay. Basically like we've been doing here. Okay. So we need to do the division first, and then we can basically do what we've been doing before. Now, because we need to do the division first, we can't put the division into our sum variable. We need a new variable for that. So we have this ready. Hopefully, no, no, that one. Cool. All right. So we have our sum real. We have our I iterator. I don't know what is going on. Let me just do this. Merge visible. Cool. And now I just want to create 2 more variables. One for, so let's call it division real. Okay. And I don't actually need to set this to 0 because I'm going to store an answer straight into it, but I'm just doing it for sanity. And division imaginary. Okay. That's funny. Okay. So I've got the sum real and I've got the division real. Now I can go into my for loop like I did before. Okay. Why did I make that so big? I have no clue. I less than n, I plus plus. And our complex addition is going to be very similar, okay? So we know we're going to have to do our division, okay? And then we're going to have to do our complex addition. Okay? And it's going to be very similar to before, except we're not adding our zi, zr, we're not adding this part. We're adding the result of the division. Okay? So whatever the result of the division is what's coming in here. But in terms of the summation, that's going to be exactly the same. Okay, we're still just summing up values. So here we're going to have some real, some imaginary. Ignore the next one, ignore the next one, and then the address of some real, address of some imaginary. Okay, just like before. But what's coming in needs to be the result of the division, which here we call dr and di. Okay, but you're going to put proper names there. Okay, so we can just put division real, division imaginary. Okay, so that's going to be the result of this. Now, if we know that that's the result coming out of this, what should be the last two, 1, 2, 3, 4, 5, 6, what should be the last two arguments for this? Remember that we need the address of where we want the result. So I'll ask you, chat, what should be the last two arguments here? Okay. So have a go. If you don't know, say don't know. Beautiful. Yeah. So it's going to be a division because that's why we created that variable for our division. And so the output's going to be our division. Okay. The input, we've got 1 plus 0j divided by our real part plus our imaginary part j. So this is going to be 1. This is going to be 0. Then we've got our, what do we have over here? I think we call it ZRI. And then we have our ZII for our imaginary part. So we've got 1 divided by 0 divided by our ZR. We then get the result of that, and then we add it to our sum. Then we just keep adding that to our sum. It's working. Okay, it's doing what we wanted. Okay, and you can see the similarity between them. Okay, the difference is that we don't just put the zk straight in. We have to put the 1 over zk straight in. Okay, which is here. Now, this last bit, which I accidentally deleted, doesn't matter, I'll redraw it. Okay. Okay, so a little bit of mathematics. If you've got a to the -1, that's exactly the same as writing 1 over a. Okay, so this this whole thing raised to the -1 is not part of the summation. Okay, it happens after the summation. Everything gets summed up, and then we invert it, or we raise it to the -1, or we 1 over it. Okay? So this can't be in the for loop, it has to be outside, and all that is going to be is our complex division, such that we have, remember that I said a to the -1 is the exact same thing as 1 over a. If this is a complex number, then it's 1 plus 0j. And we're doing that with our sum real, our sum imaginary. It's a comma. And then we just can put the result in our sum real and sum imaginary. I can't write it anymore. And sum imaginary. And we've got our answer. And now we can store it in our nth position. Okay, just like we did with this one. Okay, and each one of these can be inside of a choice. Yeah. If choice is blah, else do this. Yeah. And you can move the variables around if you like, but they're all in scope. I don't mind. I actually prefer that you create a separate sum for each one, because really this sum isn't dependent on this sum, and this sum isn't dependent on this one, so they're actually different variables. But if you want to declare sum up the top, I think that's what I suggested. That's perfectly fine as well. Either way, I'll be happy. It's more that you understand what's happening here and you've got a good comment to explain it. We all good? Does that make sense? A little bit confusing, but if you follow the maths and understand that, yeah, this is the 1 over zk part, this is the plus part, and this is the raised to the -1 part, where this here is the zk plusing. And that's basically it for part 2. Once you have that, everything should work if you've done it correctly. And if not, you can keep debugging it until you get the right answer. And this is why we included some worked outputs so that you can compare them against yours and you can see where your problem exists. Because, for example, if your division's coming out wrong, printf here, test it. If it's coming out wrong here, printf, test it. It's coming out wrong here, printf, test it. Okay, and that gives you part 2 of the assignment. Okay, that part isn't worth that much. It's worth 10%. The last part is worth a little bit more. That's part 1. That's part 2. That's part 3. All right, so just a couple of other things with your assignment that I'll mention. Oh, that was a screenshot. All right, so this is important, and this is the constraints of your program. So just make sure you follow these. I should have made that a little bigger, but it's pixelated. All right, so pi needs to be 11 decimal places in your program. We talked about that already today, so that should be easy. You're only allowed to include the standard io.h and standard lib. There is no con.io and there is no math.h. Okay, you don't need it, and so we're not including it. Okay, so it means that no one gets any unfair advantage by using the math library. You don't need it whatsoever in this problem. Okay, and you will lose I think it's 60% of the assignment if you do use it. You cannot use goto. Formatting needs to be exactly as specified. So that's talking about the tables. Text to the user needs to be easily understandable. So you can change the text to the user. So for example, when you're asking the user to enter the choice or enter the number of components, you can change that around and you can put it in your own words. You can, I don't know, as long as it's readable, it can be a little bit funny. It doesn't matter. As long as it makes sense and it is suitable for a reader, I don't really have a problem with that. Just don't put extra new lines. Okay? If there's only one new line, then only use one. If there's two, use two. Print your student number, name, and assignment. Must print the password as specified. So as specified is talking about part 1, part 2, part 3. Must be done using ANSI C and compile, blah, blah, blah. This is the big one. And this is the hard one. Okay. Code must not crash, okay, or have the potential to crash due to a Stack Overflow or segmentation fault. Now, this is going to be hard for you to judge, okay, and this is where you really need to understand your code and make sure that if you've got an array that's 3 long, you never go to this one, because you might not be able to find that mistake, but it still has the potential to crash. So you need to go through your code very carefully and just make sure that you're not accessing indexes that are outside of your arrays, because I have seen that already, as I talked about in the first part. Types should be used appropriately, so don't declare everything as a double. Obviously, the components themselves are ints. They shouldn't be doubles. Variables should be limited to an appropriate scope. So if there is a specific scope that a variable should be in given your program, and you've written the program such that it could be limited to a scope, it should be. Okay, and there's marks for that this time. There wasn't in assignment 1. Use comments to explain significant. Use comments to explain functions and solution. Yeah, don't need heaps of comments, but significant lines are expected. Why am I going down? This isn't the assignment sheet. I didn't copy it. Cool. And there's a lot less marks for us for commenting this time, but it's still significant. Yeah, so any unsafe behavior, you automatically lose 5% on top of the marks that you lose for the implementation. All right. So, did we want to talk about the lab this week? Just trying to think if there's anything else for the assignment that we need. Is there any other questions on the assignment? Oh shit, what happened there? Why did it do that? Sorry, I've accidentally hit something. All right. Okay, so I'm gonna have a. All right. So let's have another break. This has been a lot of talking. So 8-minute break. Go get a drink or something. If there's any more questions about the assignment, put them in the chat. And also, yeah, we'll go through the lab otherwise or after. Okay. Cool. All right, so let's do this. Where's me thinking? This. All right. All right. So let's go through the lab then. It doesn't appear to be any more questions on the assignment. So let's talk about the lab. And we'll learn structs as we go. Now I've lost the lab again. My printer's turned on for some reason. All right. So Let's have a look at this mechanical problem. So this is a little bit of mechanical engineering with some gears and stuff. It's kind of cool. How do I zoom down? So there we go. Better. All right. So basically, in this task, we have a more complex structure. We have this 2 gears and this belt. Okay? And there's different types of belts. They have different pitches, different tooth height, different belt heights, etc. And the thing with this is that we need to be able to represent this in our code. Now, for example, one belt here has all of these parameters, or what you say? It has these values, okay, that describe it. But the problem with this is that how would I group these together such that I just want to describe AT5 but have information here? Okay, and this is where a struct comes in. Okay, it's a little bit similar to an object, but not quite. It's kind of can be seen that way, but it's a structure, so it includes multiple bits of information. And this is really handy for describing complex data structures, such as a belt. Okay, a belt is not an int, it's not a float, but it's a collection of different data types. Okay. So that's the first thing. Okay. And what are we doing in the first part? We're actually going to. All right, cool. All right, so in the first part, we're just getting information from a user. Okay, so we don't have to care about calculating the size of the belt at this stage. But I'm going to give you this part now. Cool. All right. So here we now have a simplified model of our system. So we have one gear, another gear, the distance between them, and then the belt would go around that. Okay. Now, in terms of what's happening here, we have a whole bunch of stuff happening. Okay. And they're not simple data types anymore. Okay. So I've already designed the structures for you that you need. Okay. So we need gears, okay, which have both a diameter and a pitch. Okay. We have a belt. Okay. And the belt itself has a type. Okay. And then we have the entire system, which includes a belt, 2 gears, a center distance, and also the belt slack. Now, don't worry about the belt slack too much right now. We'll talk about that later. But you can see how this whole system is built of more complex data. Okay, so you've got this belt, which isn't just an int anymore. It's another struct inside it, and that includes a bit of information as well. And that's made up of a string, an int, a float, and a float. This is made up of an int, this is made up of an int, and the system is made up of 2 bits of complex data and 2 simple bits of data, which are just 2 floats. Okay, and we can see this system here. Okay, so with our structs, they can be in arrays, they can be pointed to, they can be used like a normal data type. Now I'm going to show you a couple of things with this because this is where most students get confused. All right, so let me go here, and copy this across. Let's go to the steps. All right, so the steps. Oh, look at this guy. So you would have seen that with the assignment, except for you would have had 11 decimal places. Now, you'll notice this as well. We've got string.h. That should be a lowercase s. I need to fix that. And then we're going to create the structures. Now, the way I like to do this, and this is the way that I usually design stuff, is I like to design all the structs beforehand such that they just act as a new data type rather than creating them when you're creating a variable. Okay. I think this just makes it easier. And this is the way that I'm going to do it. But Rick shows some alternative ways in the lecture, so you're aware. Okay. So what I do is you've got your hash includes, blah, blah, blah. You've got your hash defines. Then here, you'll have your struct definitions. And then below that, your prototypes. And then below that, main. And then below that, your functions. Okay. And this is usually the way that I will lay it out. So let's go have a look at one of these, and I'll probably pick one that's easy. The gear is probably the easiest one, so let's do that first. Now, structs are a little bit difficult in memory, so we're not going to worry about them in memory for this subject. They're actually a little bit more interesting. If you're interested, you can look it up, but don't really worry too much about it. So this is what a definition looks like. Now, this is not a variable, okay? And this is really, really important that you understand this is not a variable. It's just a definition of this struct, okay? So you can think of it like a template or a data type, okay? So for example, we've got int, that's a data type. We've got struct gear spec, which is another data type, okay? So what we're going to do now is we're going to go into main. We're just going to have a play with this, and then we'll continue back with the lab. Because this is kind of important, and this is where most students get confused. But if you understand this, it makes it so much easier. So we've got int main, blah, blah, blah. Anything else? No. All right, so let's go back to week 1. Int A. Okay, now I go back to this quite a lot, and I did this with the pointers as well, because a lot of things revolve around this concept. And if you understand this well, okay, and I know it seems so simple, but if you use the simple things to help your knowledge of the more complex things, it makes things so much easier. And the same applies with physics, biology, engineering. If you understand your fundamentals, then you understand everything. And this is why in engineering, we focus so much on the fundamentals rather than the really complex stuff. Because if you have a good understanding of the fundamentals of physics, mathematics, programming, logic, problem solving, you can solve any problem. And same with IT and communications. If you have a good understanding of maths, programming, memory, server architectures, etc., and networks, and all the base fundamentals, then you can create anything, and you become unstoppable. And you become very, very employable as well. So here we have type, and then we have the identifier. Okay, and then a semicolon. And that's it. That's a declaration. Okay. Now, this is the most common mistake that students make when using structs. Okay, so this is our data type. The type here is struct gear spec. Gear specs. Okay, really should make that. Whatever, doesn't matter. And then the identifier might be gear 1. Okay, so here I've created a variable called gear 1, and its type is struct gear specs. And this gets really confusing for a lot of students because they're like, there's a bloody space in between. How does this work? Okay. And it gets really annoying because we've never seen a space in the middle of a type. But this type has a space in between it. Okay. The struct is part of the name of the type. Okay. And it's important that you don't get scared by this space here. And a lot of students do, and they'll just write gear specs, but it's not. Okay. The whole type is struct space gear specs. Okay. Now, our gear 1, we can use it like a normal variable, but it has some problems. Okay. Or it has some features more so. Okay. It's not an int, it's not a double, so we can't do something like this. Gear 1 becomes 2. Okay. It won't work. But it has 2 ints inside it. Okay. So it has 2 ints inside it. And we can, yes, you can use a type def, but I'm not going to go into that because I think it's better to understand the syntax rather than simplifying it to get rid of the understanding of syntax. So if you're comfortable using type defs, yes, you can. But I actually prefer teaching it without type defs because I think it adds to the understanding of syntax. So it's just a question in the chat. So now I forgot what I was going to say. And my nose is itchy. All right. So what we're doing here is if I wanted to set, say, gear diameter to 4, I can do that. And this is called accessing the member. Okay. So you write dot gear diameter. Okay. And I can, I don't know, put 2 in there. And then I can go gear 1 dot gear pitch and set it to 4. Okay. And I can create another gear if I wanted to. Okay. Just like any other variable, I can do this. I can also initialize. So I can do something like this. 4, 4. Okay. And I give it the values 4 and 4 right from the start. Okay. So if I wanted to do a printf, I can do that. Okay. And I could do printf cent d gear 1 dot gear diameter. Okay. Does that make sense? so far? Now, if I want to do a scanf to store stuff in here, with this, you need to be a little bit more careful. Okay, so with the scanf, we want to store the result in the gear, let's say gear pitch. So here I need the address of, and I'm going to use brackets. I'm going to say gear2 dot gear pitch. Now, the reason for the brackets is because I don't want the address of gear 2, but I want the address of the pitch. Okay. So this is something you need to get careful with and be careful with. All right. Is that making sense so far with structs? Okay, so it's just a special data type that can have multiple types inside it. And we'll talk about arrays. So if it's making sense, just thumbs up, a little animal, or yes. Cool, cool, cool. So because this is just another data type, we can use it like we use it for creating arrays or really anything like we do when we use any data type. So actually, we'll go back to our basics. So if I want to create an array, I can do something like this. Okay. And here I have type, the identifier, and then the size of the array. So I can do the exact same thing with my struct as well. So I can do struct, gear, specs, and then I need to give it a name. A lot of people forget about this. I'll call it gears, and then 3. Okay, remember that this big thing here is the type. Okay. Then we have a space, and then we have the name, and then we have the brackets. Now, this gets a little bit more confusing because now we have 3 things in an array that can have 2 things inside them. Okay, so each one of these gears can have both a diameter and a pitch. Diameter, pitch, diameter, pitch, diameter, pitch. Yeah, which is really, really powerful and really, really handy because most objects in the world can't be described just by an int or a float. And we don't want to have to create these complex data structures that we need to make sure that these two are together. Okay? These two will always be together. They're both at index 0. They're both at index 1. They're both at index 2. So they kept together and we don't have to worry about them. Okay? So this is the really nice thing about structs. Now, if I want to, let's say, set... Now I've lost my pen. It's gone crazy. If I wanted to set, let's say, the pitch of index 0, then I could write something like this. Gears 0 dot gear pitch becomes 4, let's say. And it'll set it to 4. Gears 2 dot, what's the other one? Diameter? Diameter 2. That'll set that to 2. Okay, so we can use arrays as well. Does that make sense? Cool. Now let's talk about strings. Okay. So early on, we would have seen this, %s, okay, which is a format specifier for strings. Okay. And we haven't really used strings that much so far. But let's say I've got something like car, a, hello. Okay. Now, this string, and this is the important thing to really understand, okay, and this is the fundamental thing that defines a string and how it works versus a collection of characters, okay, is 6 characters. Okay. Now, I know you only see 5, which is the H, the E, the L, and the O, but all strings, okay, will always have a null terminator at the end, which is /0. Okay. And when you use these double quotes, it automatically always adds that to the end. Okay. And that is important for strings. Okay. Because it tells us where the end of the string is, and it tells us a lot of information for our strings. And we need to keep this in mind when using strings. Okay. So why I'm saying this is because we're going to use scanf with strings in this problem. And we're also going to do a string compare. So our scanf is going to take a string, okay? And we need to create that string beforehand. And it says it needs to store 5 characters. And you'll notice the options are AT5, AT10, AT20, which are only 4 characters long, but we need to store that null terminator. Okay, so car, I'll just call it str for now, and I will make it 5. Okay. And then here, I can just put string. Now, why does that work? Okay, I don't need the ampersand here because, remember, str points to the start of the array. Okay, so it tells me this is where my string is going to go. Okay. Now, there is one other thing we usually do with scanf with a we're not doing gettr, so that's fine. Don't worry, actually. All right, so the next thing is with printf. When we use %s, yeah, we print out string. If it has this here, it'll work perfectly fine. And when we do a scanf, it will get it perfectly fine as long as we've got that extra space to store that character. If you don't have that character here, the null terminator, and this is not null, it's the null terminator, the printf doesn't know where the string happens. And what happens? So let's say we didn't have a null terminator here. What it'll do, it will do one of 2 things. It will either print hello and then random garbage and then crash, or it will reach another null terminator in the data, which is usually, well, not usually, it is a 0, and so it will stop at that and print hello, a bunch of garbage, and then stop. And there are your 2 cases. It will either crash or not, but it will usually print out a bunch of garbage. Okay, so that's what makes a string, is this null terminator at the end versus just a collection of characters. Okay. All right. So that's our string stuff. The other thing with string, and I'm not going to go through this because we don't really use strings that much, and I don't really care about strings that much. if you do have two strings, okay, so car A, hello, car B, hello, and you do something like if A equals B, that's false. Okay, and why is it false is because you're just comparing the memory addresses. Remember, A is a pointer to the starting memory address, B is a pointer to the starting memory address. Rick will have a lecture that has all the different string functions, but the only one we care about for this lab is string compare. Okay, and if they are equal in terms of their characters, it returns 0. Okay, and this is how we compare strings. Okay, with this string compare. All right, so let me just copy some of this lab across, and then I'll show you where that stuff is, and then yeah, that should be enough to get you going. Let me just check my phone. Blah, 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 blah. Cool. All right. So it gives you 3 of the 4 structs that you need to create. You need to create the last one, which is the system one. Create main, below the structure definitions, create an array to store the different types as belts as follows. So we've got struct belt type, which is the type, which is this one. We've got the name of the array, which is belt types. We've got the square brackets, 3, okay? So we've got literal 3 there. You could put a macro if you like. And then we've got an array, okay? And we've got an initialized array. So here, we've got the outer brackets here, which are talking about the array, and then the inner brackets, which are talking about each individual structure. And they're separated by commas. Now you'll notice this AT5, you'll notice you've got car, belt name, and it's got 6 there. This one here has 4 characters. Okay, AT5 and then the null terminator. But it's stored in 6, okay, because it should be able to store any of these. And then we've got the int, then we've got the float, then we've got the next float, and I left a line in there for some reason. Who knows why? And then I've got int, float, float, int, float, float, and the strings. Create a variable to store 5 characters, and then print to the screen, select the belt type, and store the user's input into it. So that's the string that we just talked about. Copy your search function from lab 6 and make the changes as below, and make sure to comment the changes. So here, things are going to be a little bit more different. So let me grab this. Damn it. Cool. So we've got our search function. It looks similar to before, but we've got this string compare here instead. Now, the other thing you'll notice is that we've got struct belt type star here. Okay. Remember, with our pointers, if we want a pointer to a type, we have the type, then a star, and then the identifier. Okay. So we can have pointers to structs as well. Okay. Now, what you'll notice here is that we dereference the struct before getting the member inside of it, which is the belt name in this case. And the search is just as before. Okay, we're using pointer arithmetic here. If you wanted to use square braces, you could. And then we return the index like we did in the previous lab. And then what have we got? And from there, what have we got? We have, go back to main, call the function by sending the belt types array. Okay, so this one's accepts an array. Don't forget that whenever you see a star, the pointer can be to an array. Okay, so this is an array of values. We've got n and we've got our search value as before. But you'll notice that our search value is a string this time. Okay, so it's an array of characters ending with the null terminator. Handle the case of the function returning -1. Okay, so obviously if you can't find it, then you need to deal with that. Create a new variable of type struct belt specs. So this is now dealing with the belt. Set the type of customer belt specs to the correct belt type acquired in step 9. So this is a really cool step. Okay. So here we've got customer belt specs dot type. Now, if we go and have a look at that definition, dot type, this type is one of these. Okay. So you can have structs inside of structs. And we've got 3 belt types. Okay, we've got AT5, AT10, or AT20. And all we do here is the one that was chosen by the user is stored into that type. So we've got this belt spec that now has the type inside it. It has the number of teeth and the belt length. So it's got lots and lots of information inside of this one variable, not just 4 like an int or an 8 or a 4.2. It's got all of this information plus the number of teeth plus the belt length. So it's quite a powerful variable. We're going to see some even more powerful variables shortly. We're running out of room. We did run out of room. All right, from there, we set the belt length to -1. We create an array of struct gear specs of size 2, okay, which is called customer gears. We ask the user for the diameter of the first gear. So what is the diameter of the first gear? And set the gear pitch as the same as the belt. Okay, so whatever the pitch is of the belt, it gets set to the gears. Okay. You need to do this for the second gear as well. So you've got the user asking a question, you've got that scanf, and you'll notice that big bracket around everything, around that ampersand, because we want the address of this. We don't want the address of the struct itself. Create a new variable of struct timing belt system. And this is an extremely powerful variable because it has the whole entire system inside it. And then you're going to build that up. So you're going to grab the belt and put it in. You're going to grab the first gear and put it in. You're going to grab the second gear and put it in. Okay, and then you're going to get the center distance from the user. And that's where you stop, because the second task, you're going to actually calculate that. Does that make sense so far? It's a little bit to take in. How'd we go? Do we understand any of that? Was I just rambling? It's not as hard as pointers and stuff like that. It's a little bit annoying because of the obviously the type. You haven't seen this before, and remembering to put the brackets around. There are some things with the pointers that get a little bit confusing, but we're not really forcing you to use that this year. So, oh, actually, well, we kind of are, but we'll have a look at that. Okay. So we'll talk a little bit more about this in the labs. The first part's fairly simple. We will do this with pointers. There's a couple of little tricks with pointers with this. It's not as hard as pointers, the first pointers that we covered. But I'll wait till the lab to cover that. I'll have a go at this first before we talk about that. Because I think this is enough to take in right now. Is there any questions? Any problems? Any issues? Anything with the assignment that anyone forgot to ask? I think everyone's slowly leaving. All right. Well, thank you for showing up. I think this is kind of what everyone wanted was the assignment stuff. So hopefully that was helpful. Hopefully it leads to a good part 3. All right. Good luck. Unless there's any last minute questions, what I'll do is I will go have a 5-minute break, and if there's any questions in that time, I will answer them. Otherwise, we'll end it there. Okay, just where's the all right, cool. I think there's no questions. All right. All right. Thank you for watching, and that's it. Oh, one last question. Should we use complex multi and subtraction? I don't think you need subtraction at all, but you will need multiplication. Yeah, you'll definitely need multiplication because you're doing Ohm's law. Hopefully you can hear me. Yeah, so you don't need subtraction, but you should include it so that if it needs to be extended, you can. So don't be scared to include it. But yeah, it's not necessary to actually call it. But you do need multiplication because you've got Ohm's law for your current and voltage, and that will involve division and multiplication again. Okay. And try and use your functions. Try and not do it outside of your functions. Does that answer? Yeah. Okay. Thank you. Cool. Cool. Any other last minute questions? Okay, man. All right, cool. I will finish that off there.